for Pluto didn't have a really good image and just had Pluto not yet explored. And now that we have explored it, they just came out with a set of Pluto stamps and a fully complete set. So if you want those, get them quickly because they're selling out fast in the post office.
So you have to go to the U.S. Postal Service. Can you get them at a grocery store or anything like that?
I'm not sure about the grocery store. I had to go to the post office.
I would say go to the post office to ask for your Pluto stamps.
Yep. And there's incredible imagery not only of the planet Pluto, but of its moons, and they discovered some new moons, which is what Suzanne is here to tell us about tonight. And for those of you who don't yet know Suzanne, we met many years ago when she was the Education Programs Director at Fisk Planetarium at CU Boulder. And now she's working for Western Governors University. And that is an online university that was created by, was it 16 different state governors? 19. 19. Anyway,
almost 20 years ago. So we're going to have our 20th anniversary next year. And it's nonprofit and private. So don't confuse us with some of the other ones you've heard about. This is legit. Most of our funding comes from the Bill and Melinda Gates Foundation, from corporations like Hewlett-Packard. It's not, there is tuition, but it's really low. Yeah. So we're not into it to price gouge students.
And there's actually, they have excellent education programs for teachers who want to continue their education and go for their master's degree. And Western Governors is actually educates more than 10% of the STEM educators K through 12 nationwide. And it is the #1 provider of STEM teachers for middle school and high schools.
Dang. Wow.
Yeah. And Suzanne herself is responsible for half of the earth science educators getting their master's degrees.
Thank you. So if you are a teacher, or you know someone who wants to be a teacher, I teach both undergraduates and graduate students. And the average age of my students is 37. So you don't have to worry about being the oldest one in the room, because it's just you and me on a phone or doing Skype or whatever. It's the anti-MOOC. A MOOC is a massive online open course where there are thousands of people and one person lecturing. No, this is the opposite. It's one-on-one instruction, which is wonderful.
And now onward to Pluto.
All right, thank you so much, Andrea. And I want to thank everyone at LTO. I had a challenge getting here today, and the entire LTO group came out and literally rescued me. So especially John Ensworth, thank you very much. And it is really great to be here yet again, because as Andrea mentioned, I've been coming here every June, and you're stuck with me every June until Minta tells me to stop. And it's a pleasure. Why? Because I adore this community, because your community supports your community. Everything around you has been built by volunteers and maintained and operated by volunteers. And if it wasn't people, like you, and now I'm gonna get this wrong, is it Bob and Carol? Tom, I apologize. Tom and Carol, see what you started? Look at how full this room is and how expanded this facility is with 2 sets of telescopes and the marvelous radio telescope that you have. You can see the chart over there. So this is the radio telescope work. You guys have really branched out, and LTO will only continue to grow because you have community support and support it through the scientific, cultural, and whatever district that is, arts district. But this is good. This is good. So thank you. See, I'm not a paid presenter because I can't get the name straight. So yeah, let's talk about Pluto. Can you hear me okay in the back? Okay, because normally I bellow, and this time they gave me a nice microphone. So what I'm going to do is open it up to questions. So every couple of slides, yes, I'm going to take a question. Go for it.
Who named the moon?
We're going to get there. So I promise you will have the answer to that. in about 5 minutes. So we're good. All right, so let me advance the slide. And as Andrea pointed out, the New Horizons mission is Colorado homegrown. Alan Stern with Southwest Research Institute is the primary investigator, but lots of people throughout Colorado, not just at the University of Colorado at Boulder, but at Lockheed Martin and Ball and Boeing, and lots of people at the community colleges, right? I was part of the space grant stuff when we first started talking about would there be a mission and how would we educate about it. So whether people were directly or indirectly affiliated with the New Horizons mission, this is huge, and the entire state, everybody knows somebody who worked on this, and it's wonderful. All the components were designed and built and engineered here, and it is still operated by people here in Colorado. So this is a Colorado mission. It launched 10 years ago. That's older than some of you guys in the audience. So 2006, and it took 9 years to get to Pluto. OMG, that's a really long time. And as Andrea pointed out, because the data is so high resolution and the spacecraft is so far away, we want to make sure we get the best images. So we're taking the slow road. So it's taking a long time for this data to come back to Earth. We're hoping we'll get all of the data by December 2016. Guess what? That's a few months from now. So I'm hoping that over the next 6 months, we'll continue to get really wonderful press releases and lots of eye candy. Some of the eye candy was unexpected. In April 2016, there was another Kuiper Belt object that the New Horizons spacecraft happened to be flying past. I was like, I'll take some pictures and send them back to Earth. So that's what the New Horizons spacecraft is doing now. Because it's not like it went to Pluto and stayed there. It zoomed past and went, oh, look, Pluto, bye. And then it had to keep going. So it's going to continue to take pictures of stuff that we don't know about. And that's the exciting part. New Horizons is an explorer. We have no idea what the next set of images are going to be, whether it's of Pluto or other objects, which is great. If funding is approved, I'll talk about funding later, then the next planned place to be is asteroid 2014 MU69. A word about that. If it looks like a year, boy, that looks like the year 2014. It is. That's when the asteroid was discovered. So when we use things like 1994 or 2014, that is in fact the year that object came to human attention. And then, as we get a little closer, you see the M and the U. Well, there are 26 letters in the English alphabet. There are 52 weeks in a year. So every 2 weeks gets a letter. The first 2 weeks of January are A, the next 2 weeks of January are B. And so what month do you think M was?
Halfway, more than halfway through, or approximately halfway through. Plus, if the U.
Through the year, right. So M would have been what month?
July.
June or July. And then U is you take that 2 week period and you subdivide that into 26 little things. So yeah, it probably was late June or early July when this was discovered. And it was the 69th object discovered on that day. We are using computers to help us look for near-Earth objects because these are potentially hazardous asteroids. We want to make sure nothing's going to hit Earth. We want to make sure nothing's going to hit our spacecraft, even if they're very, very far away from Earth. So we are constantly looking for stuff. And so we're actually discovering hundreds of objects every day. You just don't hear about it, but it's happening. And that's a good thing. So if all goes well, then observations of 2014 MU69 will start in 2018, and that project will continue for the next year and a half, 2 years. That'd be great. We'll have to see what happens. And as I'll get to later, the decision time is getting really close. So some of of you have played this game with me before, and if you have, please let others shout out answers. But for those of you who are new, this is from John Spencer, who's another one of the Boulder-based primary investigators on New Horizons. And 10 years ago, he was trying to make the case for what is a planet versus what is a dwarf planet, and should we even have dwarf planet? How do we know what's where in the solar system? So just from looking at this chart, well, first off, can you name the planets that are in our solar system? And if you can, where on this chart do you think they're located? Now let me give you a clue. Diameter is how big across the object is. So if it's down here, it's a really, really tiny thing. And if it's up here, it's pretty big. Similarly, the semi-major axis in astronomical units, oh my gosh, what is that? An AU, so 1 AU is 1 Earth-Sun distance. So if you're at 1, that's your clue, go look for Earth. And then look for somebody who's 10 AU or 100 AU. And that gives you an idea of where things are in our solar system. So can I have someone under the age of 15 tell me, where is Earth? And okay, if you use this little red, see that little red dot? Okay, go point at it.
Like right there, that little one?
Well, except that Earth's a bit bigger than that. So can you go higher up, please? There you go, you found it, that's Earth. Excellent, thank you. All right, so we have the Earth-like planets over here. What are these guys?
Jupiter and Saturn, maybe.
Yes, and notice Jupiter is the largest object in our solar system other than the sun in terms of diameter and in terms of mass. So look how much bigger Jupiter is than Earth, and look how much further away. Jupiter is actually 5 times further away from the sun than Earth is. So what's the planet after Jupiter?
Saturn.
And then?
Uranus.
And then?
Neptune.
Aha, and where's Pluto? Okay, so wait, we're gonna get there. But this is why we call these the classical planets. The Earth-like terrestrial planets and the Jovian Jupiter-like planets, because you can really see they are different from everybody else. No, I'm happy about this because I'm a planetary geologist and I'm about to show you a trick of the trade. Let's look at things that are round. If they're round, they're spherical, like a globe. So they're above this red dashed line. If they're lumpy and bumpy, like a potato or a peanut or a dog bone, then they're below that purple dashed line. Notice that there's some stuff in between, because then we get into the argument of, well, how round is round? And if it looks like an Easter egg, is that round? Yes. But we had to have an in-between category, so that's in between those two. So now can you find Pluto? All right, you're sitting here, so you have to help out. Do you see this little red thing? Okay, so you're going to point at it, and you're going to tell me where, well, first off, yeah, what's that clump of stuff between Earth and Jupiter? So bring your pointer down a little bit. Okay, hold on just a sec. I'm going to yeah, go down a little further into the purple area. There you go. What's all that? Do you know? Who wants to guess? The asteroid belt, full of asteroids. Good. Now move it over a little bit further to the right. There you go. What's that stuff?
Meteorites.
No, more asteroids was the correct answer. So that, but good choice. Thank you very much for your help. So we have 2 parts of the solar system full of small, irregularly shaped objects, and as you can see, the occasional above the red line set of objects. Now, there is a part of the solar system called the Oort cloud, and I'm going to be really evil. Do you see this little red line here? Right there? Can you use that and point out, where's the Oort cloud? Where are you pointing? Actually, keep going to the right. You're going to have to go off the chart to the right. So go to the bottom chart. Yep, go to the right. Keep going. Go off the chart. There you go. The Oort cloud is more than 1,000 AU. In fact, parts of the Oort cloud are 10,000 to even 100,000 AU. 100,000 Earth-Sun distances is 1 light year. That's a distance it takes for one little packet of light energy called a photon to go from the sun all the way out during 1 Earth year. So if it left on January 1st, and this is December 31st, that's how far that went. That's 1 light year. That's the edge of our solar system in terms of the Earth's gravitational pull. You might have seen some things that, oh, but Voyager 1 and Voyager 2 have left the solar system. Well, they've left the protective bubble of the sun's magnetic field, but the sun's gravity is still out there. All right. Thank you very much for being a biohazard with the laser pointer. No, I'm teasing. You're fine. Thank you. Okay, so we still have to figure out what's going on with Pluto. Do you mind if I jump ahead a little bit? Anybody like watching Peter Dinklage? He was an elf. He's on Game of Thrones right now, but he also hosted Saturday Night Live recently. Do you like Peter Dinklage? Yeah, he's one of my favorite actors. Peter Dinklage is a person. We all agree on that, right? Is he the same height? Is he as big as other adult people? No. But he's still a person. He's just a little person. Pluto is a planet. It's just a small planet. It's a little planet. And politically incorrect, they call it a dwarf planet because we have dwarf galaxies and dwarf trees and other things in science are called dwarf. So don't apply that to Peter Dinklage. That would be rude, but you may apply it to Pluto. Pluto's cool with that. So we have dwarf planet Ceres, the very largest, most round object in the asteroid belt. And we have Pluto and Eris. Eris was discovered in 2005, and because she caused all the chaos, she was named for the Greek goddess of chaos and lawlessness. And so her moon, Dysnomia, is lawlessness, Eris is chaos, and these two are among the largest, roundest objects in the Kuiper belt. But there are lots of other dwarf planets there. And there are more dwarf planets even further away into the inner Oort cloud and the Oort cloud itself. So I love the fact that Pluto is a dwarf planet because it's the very first of a whole new class. And there are so many more of them. So all these worlds to explore. And they are, in fact, worlds. So if we compare their sizes, we've got Mars, which is a planet. And then we have Mercury, which is the smallest planet. And then we have Earth's moon. And then we have Ceres, which is the smallest dwarf planet that has a name. And then we have things like Vesta. Hey, do you guys remember the Berthoud meteorite from a few years ago? So it's been confirmed because the Dawn spacecraft went to Vesta that the Berthoud meteorite is a chunk of Vesta. And you know what else? That Vesta is probably a dwarf planet. And so it's not officially named, but it's like one of these guys in between the purple and the red line. And in my book, Vesta is a dwarf planet. So you have a piece of a dwarf planet. And if you've ever touched the Berthoud meteorite, you've held a piece of Vesta in your hands, which is cool. All right, so I'm not going to belabor this point because it's hot and we have other stuff to do. But it's up here if you want to look at the names and the shapes. Now, these are not images. A lot of these are artists' renditions because, yes, we've been to Ceres, but, you know, this particular diagram was made before we got to Pluto. So they were guessing here. But these are the relative sizes and the relative shapes and the relative colors. And remember I said there was an Easter egg one? That's Haumea, the Easter egg dwarf planet. So we're still arguing over how round is round and what do you call these things. So John Spencer had made these arguments to present to the International Astronomical Union and try to convince other professionals about these categories. And the vote held by the IAU was on the last day of the conference after people like John had left because they had to go back and teach their classes. So the vote was held without the people who should have been there. And there was a lot of arguing back and forth over the course of 2 weeks as to what to do and how to do things. And a lot of people came away from that very unhappy. So I was just talking to someone yesterday. We were driving, and he said, "What is your talk about?" And I said, "Well, you know how that thing over there is an alley, but we're on a street, and we're approaching a boulevard? And if you know what these words mean, you know alley is relatively small, and street is kind of, middle of the road, so to speak. And boulevard is a bit bigger, right? But you have a sense of what they are because you know what the words mean." This was an attempt to, for the very first time in Western science, define what a planet is. And they goofed. They got it wrong, in my opinion. Because these are terrible definitions. People don't agree on them. We don't know what some of this stuff means. And it doesn't give us a sense of what's going on. Because in the 10 years since this very, very bad first attempt, the International Astronomical Union won't bring it up for another vote. Because they're kind of scared now. Because not only do we know a whole lot more about our own solar system, we have discovered, thanks to the Kepler spacecraft, more than 2,000 other planets in solar systems beyond our own. This is a terrible definition for our own solar system. How are we going to apply it to others? And then somebody said, well, this is only for us. I was like, well, that's dumb. So it's dumb. So hopefully this will get changed soon. But this means this is why you haven't been seeing it in your textbooks, because nobody wants to publish this. And if it is in your books, it's going to change. So don't get wedded to that textbook. So let's look at what's really going on. Now, I have to apologize. I didn't update it for this month. But last month, when I was starting to put this talk together, on May 21st, I went and I checked Mike Brown's website. Mike Brown and his team, those are the guys who killed Pluto. Because they're the ones who found Eris and got this whole argument going on. So on his website, which does update every day, as of last month, there were 10 objects that were nearly certainly dwarf planets, beyond the ones I've already mentioned. There are 5 that we know exist because they have names. Then we have these 10. Then we have another 26 that are highly likely. And it's all based on this definition of being large enough to be round. If you're, well, like me, an oblate spheroid all by yourself, you get to be a dwarf planet or a planet. And that's the definition. Yes, I have enough gravitational mass to self-round. I'm good. But that's the point, right? We have so many of these guys. And those of you who are still in the business of memorizing planet names, how many of them do you really want to have to memorize? Okay, so I'm good with just 8, as opposed to 18 or 23 or 31 or however many it ends up being. So thank me for that. No, I'm just teasing. The point is that these are fascinating places. With the exception of Ceres, every single one we found has a moon. Even Ceres has an atmosphere made of oxygen. There seems to be liquid water in and under the surfaces of these places. Andrea?
And I believe historically, after Ceres was discovered, it was called a planet for a while.
That is true. May I digress for a minute? Ceres was discovered in 1801. Why was it named Ceres? For the Roman goddess of cereal. So those of you who eat oatmeal or Wheaties for breakfast, you are honoring Ceres because you're having cereal, or a form of cereal. And yes, those words are linked. Yes?
I don't want to put you on the spot, but what would be your better definition of a planet?
Well, the last time I got into this, we derailed for 15 minutes, so indulge me for a moment. I'm actually going to get there in the point of this talk, but for me it's all about planetary structure. So a terrestrial planet or moon of a terrestrial planet like Earth's moon has a solid core. So it has a rock or a metal core surrounded by more rock. Some of those can be liquid, some of those can be solid, but these rock and metal layers are layers, and that's pretty dense stuff. And it's all surrounded with a rocky crust, and then on top of that, you have air, so that's your atmosphere, and you may have liquids on the surface. For instance, some of the moons of Saturn and Jupiter clearly have liquid on the surface. Look at Enceladus, which is a moon of Saturn that has active warm water geysers. By warm, I mean room temperature. But still, water geysers, right? That to me, that's a planet or a dwarf planet. So give me just a minute, and I'm going to get into how do we then distinguish which is which, and a lot of it is arbitrary. I didn't get to the structure of Jovian planets, but if you have a Jupiter-like planet, you have a solid rocky core, you have a liquid or slushy mantle, and by slush I really do mean 7-Eleven slush, that kind of thing. And then you have lots and lots and lots of gas around that. So that's still a kind of planet. That's not good for humans to live on, but those planets often have moons that have that terrestrial structure I just discussed. So how do you tell a moon from a dwarf planet, from a gas giant, from an ice giant, from, right? So we could, in fact, spend all of our time subdividing, which is what we do. And remember, I'm a geologist by background, so if you really want people into taxonomy, talk to a mineralogist. They will subdivide and subdivide and subdivide mineral classes forever. They just never get tired of it. If we're talking about stamps, anybody do stamp collecting? Okay, you're going to enjoy planet collecting because you have to do the same thing. You have to put them into categories, and the categories can change depending on what you're looking for. In solar systems other than our own, we've actually found dwarf giants. Now think on that. Dwarf, meaning little, but they're just like our gas giants here. They have the rocky core, the liquid mantle, and then lots and lots and lots of gas, but they're small. We don't have that in our solar system, but we have them in other solar systems. That's exciting! I want to learn more stuff and play around and have to reorganize and throw out my paper textbooks because they're wrong. That's cool! And we didn't even talk about what's a moon, because that's really headache-inducing. Because so many moons are now effectively dwarf planet-like, or even planet-like. So what's a moon? A moon is something that orbits, not necessarily something else, but the center of mass between those two objects. And together, going around that center of mass, they go around a star. So I need a couple of volunteers from the back, please. 2 people, please. 2 young people. Come on.
Come on, guys.
I made eye contact. You have to come now. All right. If you don't want to volunteer, I will take 2 older volunteers. But I do want 2 people from the back. Okay. Thank you. Yay. Okay, so we have 2 planetary bodies, a smaller one and a larger one. And the center of mass is right between you. So can you take off one shoe and just put it right there? Because we need a marker. Can you guys see that lovely orange-red marker? That is the center of mass. So I would like the 2 of you, keeping your eyes on each other, let's make you tidally locked. I'd like you to orbit the center of mass. Okay, so yep, the small one follows the larger one, go around in a circle. So these guys are orbiting the center of mass between each other. Now, I'd like you to stop. You may put your shoe back on because you're going to need it. Now orbit me, please. I'm the sun. So wait, you still have to orbit each other's center of mass, but now you got to orbit me. Come on, do this. You can do it. Okay, you gotta come toward me though.
We are.
Okay. So, you see,
We're going to Jupiter right here.
this can get complicated.
Faster.
It's a little narrower.
It's a little narrow. No, okay, but you've proven the point. You guys are good. Thank you very much. This whole center of mass thing is quite the thing. And if we look at Earth and Earth's moon, it turns out that our barycenter, our center of mass, is inside Earth. But you know what? It's pretty close to our crust, isn't it? That's pretty close to the crust. And so if the moon moves away from Earth, and guess what? The moon is moving away from Earth. We're never going to lose our moon. But this is still a dynamic system trying to reach equilibrium. And eventually that moon is going to be much further away from Earth as it is now. What will happen to our tides if the moon is further away? There'll be less. They won't go away. 40% of the gravity for tides comes from the sun. But of the 60% that comes from the moon, if the moon goes away, that amount's going to go down. So, what do you do when you have a system like, well, okay, the largest moon of Pluto is either pronounced Charon or Charon. If you knew James Christie, who in 1978 discovered this moon, you know that his wife Charlene got the moon named after her, so it's called Charon. On the other hand, if you don't know these people, then it's Charon, because that's the correct Greek pronunciation, if you know your ancient Greek. So you're going to hear people on videos have one or the other pronunciation. Both are correct. And eventually someone will agree the Greek one is right. But anyway, so what's going on with Charon and Pluto is that there's actually a point 1/3 of the way between the two objects where the center of mass is. So, what you just saw with our two bodies orbiting the center of mass, that is what Pluto and Charon do. And then they bring in all the other little moons, and all together they orbit the sun, which makes things really wacko. And so, I have a little video for you guys to watch. So if I could please ask John to put on the video, I will be quiet, and then I will answer your question.
We talk a lot about Charon, Pluto's largest moon that is half the size of its host planet. But what about the other 4 smaller moons? They are interesting, to say the very least. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are differently fascinating than Charon. These moons are each 20 to about 50 times smaller than Charon, they aren't round like Charon, and unlike pretty much every moon in the solar system, they are not in synchronous rotation with their host planet. They don't always show one face to their host. Instead, they are spinning incredibly fast. Hydra, for example, the most distant of the 4, spins 89 times for every orbit it makes around Pluto. New Horizons mission scientists suspect these chaotic spin rates could be due to Charon exerting a strong torque on the bodies that stops them from settling into a more common synchronous rotation. But that's not all. These small moons also wobble far more than scientists expect small moons to wobble. They behave like spinning tops more than anything else. This uncommon movement could be explained by observations that suggest these 4 moons were formed when multiple smaller moons merged, which means at some point in Pluto's history, likely in the aftermath of the theorized impact that formed Charon, the tiny planet had more than 5 moons, but the smaller moons coalesced into the ones we see today. And it's worth noting that these are Pluto's only moons. Mission scientists did expect to find more moons when New Horizons reached the Pluto system, more leftover debris from the impact, but found nothing. Pluto only has the 5 moons that we discovered from the Earth.
Thank you, John. Yes, sir.
It's probably an obvious question, but why did they orbit?
Why do they orbit? That's not obvious. That's a really good question.
I've never understood why things orbit and what energy forces cause them. And that last diagram is great because you can see the spinning energy levels that are so different. Very complex.
Very complex. So this whole field of why and how objects orbit each other is called orbital mechanics. And people do get masters and PhDs and are still learning things because we do not have all those answers figured out. And if you really want to hurt your head with orbital mechanics, look at the ring particles orbiting Saturn or Jupiter or any object that has ring particles. And did anybody, you know, John, I'm going to make you look for this. Since you were on the internet, feel free to get back on the internet. We have a quasi-satellite of Earth that was just announced by NASA yesterday. And I can't remember its name. It was like 2009 something. So if you just type in quasi-satellite of Earth, which you're doing right now, there we go. And let's look for video. So I'm going to ask you to actually, there we go. Thank you. Well, this is CRUST, which we've actually known about since like 2003. And this is another one of those quasi-satellites. It's an asteroid that shares Earth's orbit around the sun. So CRUST doesn't really orbit Earth. It orbits that common center of mass, but this object has not been with Earth forever and will not be with Earth forever. It just happens to be with us right now. Think of, for those of you who are old enough to have girlfriends or boyfriends, there's the person you have right now. That may not be your forever person. So this is who we have right now. There's another object that was just announced yesterday. So I'm going to send you back to Google, go into videos, and let's see if we can find, there we go, one of the newly discovered ones. And we'll have to see if that video comes up. So what you get are these objects that enter into these temporary semi-stable orbits, but they're not really stable because these objects don't stay there for very long. So if they did, there we go, this is it, 2016 H03. Remember what I told you, so this was just discovered a few weeks ago, like late April, early May. There we go, look at that. That is a quasi-stable orbit.
How big is it?
It's not very big. It's a few tens of meters across. Now, there was some talk a few years ago that there was this unusually bright white object that happened to be the exact same length and width and height of a Saturn V rocket booster. And oh my gosh, in 1970 or 71, we kind of lost a Saturn V rocket booster because it lofted the astronauts on the Apollo missions, and then we kind of lost track of the booster. Oh, maybe same thing. Yeah, so we have some human-made objects in these quasi-stable orbits. There you go. That's it. Up to 300 feet, so that's 40 to 100 meters. So about the size of this room, actually. Or maybe the building. I'm not so good at that.
Football field.
Football field?
It's 300 feet.
Okay. I will take that as confirmation. Yes, sir?
Can a moon have a moon?
Yes. And so do asteroids.
So what's the name for you?
Okay, so here's the thing. The more we look, the more we find, and the more complex it is. So why do objects orbit other objects? Anybody remember Newton and Newton's laws of motion? And he had one called Newton's universal law of gravity, or Newton's law of universal gravitation. And remember, law is the same thing as principle. So we say law for people like Isaac Newton who lived 400 years ago. We generally say principle for people who are alive today. This is just how speech has evolved. It doesn't mean a law is better than a principle. They're the exact same thing, and neither one is a scientific theory. They just get you toward the scientific theory, which is the big explanation. So if you have your head wrapped around laws of motion and kind of sort of how gravity works, we don't really understand how gravity works. But for Newton, we kind of, he was the one who really wrote it down for the first time. Here are some mathematical formulas to explain how gravity works. And then Einstein modified Newton, and we're still working on that. So we don't have a complete grasp on how gravitational forces work. But by and large, big objects have a whole lot of gravity. And mass is like money. The more you have, the more influence you have. So if you have a lot of gravitational mass, you have a lot of pull, and objects are going to want to go around your equator. So most objects that orbit other objects are in what we call the equatorial plane. For the sun, we call that the ecliptic plane because that's where eclipses occur. And so you end up with objects starting to follow certain rules. And it's all very nice and stately until those rules get broken. Think of people who are driving on a highway. All the cars are in their lanes, everything's good, until there's a car accident. And then suddenly stuff's flying in all directions, and you're spun around, and you're driving the wrong way on the highway. That happens in solar systems too. So early in a solar system, when everything's very immature and stuff's flying around in all directions, you got stuff really crashing into each other, and that's how you can make a moon of a moon or a moon of an asteroid. You knock off a piece. And sometimes those moons are just called moons because they all end up, instead of orbiting the moon, going, oh, there's a planet there or a dwarf planet there. I'm going to orbit the bigger thing. Or better yet, I'm going to orbit the center of mass of this whole system. And so that's how that works. Did that explain something?
Okay.
I could get into a whole lot more math and physics, but then the rest of the audience will fall asleep.
Yes, my point is, when you look at the galaxy, as we've gone out, we see more and more and more. Okay, all Newton's stuff was all based on the plane we're in now. Then we got into subatomic particles, and they don't behave the same.
No, they don't.
We've lost it. So when you look at everything, and then you try to apply Newton, but now all of a sudden this whole thing is just a subatomic particle of a much bigger element. That's why
Well, no, but see, I'm oversimplifying because, as I said, most of the audience will fall asleep if I try to be more complex. But also, I didn't mention dark matter, which has even more gravitational pull than normal matter. And so you'd think, according to Newton's laws, that the further away you got from the center of a galaxy, the slower everything would go. That's true up to a certain point, and then you realize things are being affected by the dark matter surrounding every galaxy. So the closer you get to the edge, the faster stuff starts to go again. And Vera Rubin, who discovered this in the early 1970s, every December, I wait for her to get her Nobel Prize in physics. You have to be alive to get the Nobel Prize. This woman discovered dark matter. Where is her Nobel Prize? I'm still waiting. Maybe this December. But we've known about this for 45 years, and we're still trying to figure out what is dark matter, what is dark energy, which acts sort of like an anti-gravity. This is why I'm saying we don't really get gravity, because this is complex, there's a lot going on, and it's just this topic for a whole nother talk. So I apologize for blowing you off, but I'm blowing you off. Okay, so here's another interesting thing. This is a real image. This was taken by New Horizons as it was approaching Pluto. So at the time this was taken, this was our very best image of Pluto. This is from like a year and a half ago. This was our best image as of a year and a half ago. Here's Charon, and then those other moons that were discovered. Now, Styx and Hydra, notice N and H, they were discovered by the New Horizons Spacecraft, looking ahead to make sure it wouldn't run into anything on the way to Pluto. And then, as New Horizons got even closer, it found these guys. And on another slide, I will get into the argument about Styx and Kerberos. So bear with me. But let's just take a moment to go, isn't that beautiful? Okay, so this is July 14, 2015, the flyby. We got this image a little bit later. Yes, sir?
Do you know how the planets were named?
So the question is, do I know how the planets were named? The classical planets actually have different names in different languages, because if you can, for instance, say Venus in Egypt, you would give it a name in whatever language was spoken in Egypt at that time. And people in France would give it a name in French. So the classical planets have a lot of different names. The names that we use in the United States tend to be from ancient Latin or ancient Greek. So when I say Jovian, I mean by Jove, which was the name for Jupiter. So a Jovian planet is Jupiter-like because Jove and Jupiter mean the same thing. Jupiter was Greek, Jove was Latin. Other planets and dwarf planets and their moons and all the other objects that we have in our solar system we now can go to all sorts of different cultures to name moons. And I'm actually going to get to this in just a second. But one of the exciting things for me is some of these dwarf planets, we're now using American Indian names. We're using Pacific Islander names. We're using the names of deities and important people from all over the world, from cultures all over the world. We're including people of different skin tones, people who are male, female, or none of the above. It's really wonderful to be able to open it all up. And that's what we're doing. Because guess what? We have a lot of things still to name. So let's just look at this for a moment. This is in fact a real color image, but the colors have been played with so that they pop out a little bit more. And what we find is that you can't see the atmosphere in this image, but Pluto does have air. And that air is primarily nitrogen, just like ours. Take a breath. Now let it out. You've just taken in 80% diatomic nitrogen, and on about 20% diatomic oxygen, and a little tiny bit of carbon dioxide and water vapor and stuff. So if we're breathing mostly nitrogen, and this is mostly nitrogen, doesn't that make you go, huh? Can't live on Pluto just yet. It's still a little cold. But obviously not as cold as we thought, because there's all this interesting chemistry and geology and physics going on, which couldn't happen if it was really, really cold. There's a heat source. Probably from inside, probably, and I'll get in trouble because this isn't verified by anybody, but I think there are some radioactive isotopes that are keeping everything warm inside, and that explains a lot. But I have no proof of that, so that's just Suzanne talking. So, what do we know? What is verified? What is verified is we have some really familiar compounds. Carbon monoxide is the stuff you don't want in your house. It will make you very sick. Methane is also not good to breathe, but it's very good to use when you're trying to heat something, because if you have your home heated with natural gas, or if you use propane, right, that's a related chemical. So a lot of familiar chemistry here. There's even a familiar name for a certain group of people. Anybody remember Carl Sagan, Cosmos? So he and one of his colleagues back in 1979 came up with the word Tolin, which, this is ancient Greek, it really does say Tolin, and it means muddy. He actually was going to use a different word. He says right here, we were going to call it star tar, but decided Tolin sounded more scientific. And we're really glad, because I personally would be embarrassed talking about star tar all the time. But it turns out that these red areas on Pluto are in fact covered in tolins, first proposed by Carl Sagan. Go ahead.
What chemical?
Again, I don't want to get into the chemistry here, but if you take molecules like methane and carbon dioxide and you subject them to enough energy to break them apart and form them again, you make complex organic, meaning contains carbon, not from the organic section of Whole Foods. That's something else. But organic means contains carbon. So you get these carbon-based molecules that tend to be the same sorts of things that you would find in life forms or in environments that can support life. That does not mean there's life on Pluto, but isn't that interesting? There might be life we can't recognize, but the building blocks are there. Here's another interesting thing. Remember when I had our volunteers and I said, go around the center of mass, but make sure you face each other? Charon and Pluto not only face each other, they face each other, and remember you said have a string with a rock around it? Imagine there was a string between the two, so that they've aligned each other's center of masses. So Pluto's center of mass and Charon's center of mass are now aligned right along that straight line between their shared center of mass, that barycenter, so that the heart of Pluto, the Sputnik planum, this heart is always going to face Charon, because they are that locked into each other. And what's really interesting as a geologist is this area that looks like a heart is at lower elevation. So one of my first questions is, oh my gosh, they've got glaciers. How did the glaciers flow? By gravity. You go from high elevation to low elevation. And the ice moves. But you have to have the ice warmed up enough to flow. So we're still really into some interesting physics and stuff. Yeah.
What affects are the moons and the orbits and everything else in their gravitational pull?
We're still figuring that out, but it seems as if, obviously, the more mass you have, the more influence. Charon has the greatest influence on Pluto. The other moons are small and further away, so they have less influence, but they still have some influence, and we're still trying to figure that out.
Pluto doesn't spin like Earth.
The question is, Pluto does spin like Earth. Every object in our solar system has a rate of spin. And Earth, of course, is 24 hours. Does anybody know the rate of spin of Jupiter?
10 hours.
10 hours. So moons and asteroids tend to be like 5 or 6 hours. So yes, Pluto does have a rate of spin. I just don't know it off the top of my head.
That's okay. I was just curious.
Yeah, does anybody know the rate of spin of Pluto? It's not unusually fast, correct? If it was really super fast, like we saw Kerberos, or was it Styx? It was Kerberos, I think. It was spinning 89 times for every one orbit around Pluto. That's a fast spinner. But Pluto itself is not that fast.
It's 6.39 Earth days.
Thank you very much. Did everybody hear that? 6.39 Earth days. Okay. So here's another thing. If we look at another part of Pluto, so here's the heart, tidally locked to Charon. So we're over on this side of the planet. It has an area that looks like it's been stretched and thinned. Now, on Earth, we have those terrains as well. We call them basin and range. Has anybody been to Nevada? Okay. All of Nevada is basin and range, where you can see the crust of North America has stretched and thinned. It has not cracked yet, but if that continues, it will crack, and then we'll call that a rift or a rift valley. And if that continues and it fills in with water, then we'll end up with an ocean and a mid-ocean ridge like we have right in the middle of the Atlantic. Not there yet. I'm not saying this is like that. I'm saying that this is an equivalent in that you can see some stretching and thinning and cracking, and you can see some unusual stuff around the craters, and it's even tied to the chemistry. So here on Earth, we have H2O snow. We have water ice crystals, and we call that snow. On Pluto, it's methane snow. It's the same process, just a different molecule. That is so interesting. Oh, I'm sorry, I'll go back.
One thing looks like a volcano up in...
Oh, are you talking about this?
Yes.
I cannot comment on that. I think it will notice that, yeah, the little peak is off center. So there are two kinds of craters. You can have an impact crater, which tends to be bowl-shaped, or an impact crater where there was a bigger impactor with more velocity, and you end up with some rock sort of pushed up in the center. It's like the rock jumped up. So that's what's called a complex crater. You can also have a volcanic crater. And volcanic craters tend to have their central peaks or their calderas, their down part. Obviously, I'm making that weird sound somehow, so I will stop. But a volcanic caldera tends to be off-center. I can't comment. We just got this image like a month ago, so I haven't had time. And I don't think the researchers have had time to figure out if there's any volcanism or volcanic processes on Pluto. But I will say ice volcanoes are perfectly normal in planetary science. We call those cryovolcanoes. And ice is a perfectly fine substitute for rock. So if rock can liquefy, turn into magma, and then erupt, so can ice. It liquefies, it erupts, and then it freezes back. And that's totally fine. So yes, volcanic activity is not out of the question on Pluto. So we were asked about, you asked about names. No, you asked about spin rates. Someone asked about names. Thank you. It turns out that the internet, people like you, have been participating in surveys that NASA and private organizations like the Planetary Society have been doing for a long time. And you've been asking about how to, what are these things called, and can we call them something else? And the answer is yes. So for Pluto, the objects are named for spacecraft and explorers, both real and imaginary. Charon, you get fictional explorers. So on Charon, and this is what we're looking at here, I'm a Doctor Who fan, so I'm going right to Tardis Chasma and Gallifrey Macula. But if you like Star Trek, you can go to Kirk Crater. You can also notice that they have mountains named for people like Stanley Kubrick and Octavia Butler. So all sorts of interesting places. These are informal names. They have to be adopted by the IAU, which is the same group we're all not happy about. So they kind of drag their feet. But that's fine, because it means we get to keep calling this Kirk Crater for a long time. Notice what's coming up. All these small moons, as we get more of those high definition images, we're going to have to name stuff. So if you like dogs, get your favorite dogs from history or your favorite dogs from books and movies, and those are going to name features on Kerberos. And if you're into Hydra, hail Hydra, who watches Agents of S.H.I.E.L.D.? Okay, or Avengers movies. All right. So Hydra is part of that, and that's going to get serpents and dragons, and there you go. So still be part of this. I think Planetary Society and other groups will have naming contests. So who names these? You do. With one exception. Remember I told you about Charon? That stuff was already named before the internet, so you didn't have a vote. But then Styx and Kerberos were discovered just a few years ago, in 2011 and 2012. And William Shatner got on Twitter and said we should name it Vulcan. And lots of people said yes, and it won the Twitter vote. And the officials said, nope, we already have an object named Vulcan. We can't use the same name twice. And William Shatner pouted, but there we go. And that's the end of it. So that's why we have Styx and Kerberos rather than Vulcan. It was all part of a Twitter campaign. So let's get back to some science, because we have wandered a little far afield. What's with this dark stuff? Well, remember I said that Pluto has an atmosphere, and Pluto and Charon influence each other? So they influence each other to the point where stuff comes off Pluto and hits Charon, and because of the way Charon is tilted, all that stuff, those dark tolons, get stripped off Pluto and dumped onto the North Pole of Charon.
So will it eventually get smaller because of that?
No, not by much.
Okay.
Because it doesn't take much to color something. If you've ever gotten a smudge of dirt on you, especially on a white shirt, you know that it doesn't take much to discolor something.
Oh.
All right, I am getting toward the end because I know I've been talking for an hour, and I apologize if I'm tiresome. Yes, Mark?
If I was standing on Pluto, how much would I weigh?
Oh, that's an excellent question. So we'd have to know the mass of Pluto, which I'm sure somebody does. Somebody quick on Wikipedia can look up what is the mass of Pluto. And then using force equals mass times acceleration, which is Newton's second law, the acceleration due to gravity is usually written small g. So then you'd have your weight equals your mass times the acceleration due to gravity on Pluto. And then it's just a matter of doing math. 10 to the 22 kilos. I have no idea what that means. Okay, thank you. But you see, so once you have data and you have the formula, because I just gave it to you, you crank it out, you figure it out. You would, if you weighed 100 pounds on Earth, you'd weigh, okay, somebody help me out, like 10 pounds on Pluto? About 10 pounds on Pluto. Cool. Good question, Mark, thanks. All right, so what's going on with the crust of Pluto? crust of Charon, excuse me. And by the way, this is a true relative size of Charon versus Pluto. Well, remember what I just said? If you have planets with solid cores, that could be terrestrial or Jovian. If you have a liquid mantle, oh, that tips you over to the Jovian side. But now your crust is made of ice. Oh my gosh, we didn't talk about having an ice crust. And that's the thing. Terrestrial planets have rocky crusts, and Jovian planets don't even have technically a crust. They just have all that gas. So if we have ice crust, we have a whole new realm of worlds to explore. Dwarf planets and moons of big planets like Jupiter and Saturn have icy crusts. That's a whole nother category. We're right back to our stamp collecting. You can reorganize your stuff based on what the crust is made of. And so people do. So NASA scientists have been looking at, so what does this mean? Are there any craters? Because maybe we can use crater counts to figure out how old things are. And it turns out, look how nicely the data falls along this yellow line. Around 4 billion years ago, there were a whole mess of craters on both Charon and Pluto. There was some sort of impact event. Stuff fell back on both objects. And those 3 other moons of Pluto are what remains of that impact event. And yes, we're still trying to figure out the details of who was the impactor and did it completely vaporize, or are these little pieces of them, or are Styx and Nix and Hydra and Kerberos, did I say 3? 4, the other 4 moons. Are they bits of Charon or Pluto? Still working that out. Looks as if, though, some of it did come from Charon. And I love this part. In about April, there was a press release that said that the crust of Charon kind of hulked out. If you ever watch the Avengers, you know how Bruce Banner wears normal clothing, and then when he becomes the Hulk, he expands and he bursts through everything except his pants, which magically stay on. That's cool. Well, Charon did the same thing, because if you've ever made ice cubes, you know you can't fill the ice cube tray all the way to the top with water. Because water, when it freezes, does what? Expands. Exactly, it expands. So, if you have a crust made of ice, but then there was an impact or something else that could melt it, what will happen when that ice freezes up again? It expands, and that explains some of the cracks that we see. The ice crust of Charon cracked, we think.
4 billion years ago.
Ostensibly. It could have been more recent than 4 billion. The cratering event was 4 billion years ago. This cracking could be a whole lot more recent. Oh, hang on, I skipped. If we have time, or maybe later, we do have it's a 20-second flyover. So John, if you guys will indulge me, let's take 20 seconds. And can somebody tell me, what are the weather conditions? Can we look through the telescopes tonight?
Yes.
Yes, so I won't talk too much longer, because, but it's still pretty bright out.
We can see Venus.
You can see Venus, that's true.
Actually, you can't, because it's next to the sun.
Oh,
But Jupiter is in the out.
okay. Okay, well, John, go ahead and play this. So this was put together by Stuart Robbins, who got his PhD from the University of Colorado at Boulder just a couple years ago. And so here we're looking at one of those big cracks on Charon. And we're going toward a mountain with one of those up peaks that I told you about, one of those complex craters. And so we're going to watch it one more time. And what I love is that this is real data that then got turned into a computer simulation. And so as we get better data, we'll continue to have better simulations and better real images. Thank you, John. So very quickly, because the little guys we really don't know very much about, we do know how big they are. So you were asking about sizes. Charon is over 1,200 kilometers across. The boundary to be a dwarf planet, how big do you have to be to self-round, is almost 1,000 kilometers. So Charon should be a dwarf planet all by itself. But because it's orbiting the center of mass and Pluto is the biggest object, Pluto gets to be called the dwarf planet, and everything else orbiting that center of mass is called a moon. So of the smaller moons, Styx and Hydra are about 40 kilometers across, so that's about 25 miles. And then Kerberos and Styx are about 10 kilometers. 10 kilometers is about 6 miles across. So these are not big guys. There is, in teeny-weeny print, way more data. I can share that with you later. We do think that all of this happened because of impacts, but there could have been collisions. It could be that some of these guys used to be smaller and rammed into each other and became one larger moon. That's possible.
How do you know whether there would have been asteroids, or why are those called asteroids?
Well, asteroids tend to, well, everything in our solar system orbits the sun. So if you are small and irregularly shaped and you orbit the sun and you're primarily rock, then you're called an asteroid. If you're primarily ice, you're called a comet. If we can't tell, you're called a small solar system object. And eventually the words comet and asteroid will go away and everything will just be small solar system objects, because who can tell anyway? No, we can tell, but still, it gets complex and that's just easier. If you and your buddies orbit a center of mass and together as a group of friends, you go around the sun. You are a planet and moons, or a dwarf planet and moons. And that's the naming convention we have right now. One of the things we've been looking at, though, is color. Are they all the same color, or are they different colors? And the answer is, it depends. Look, I snuck in a hell Hydra. Okay, so there's a red spot on Styx. And what is this? Well, it looks like it's right around a crater. So it looks like the red stuff is just underneath the surface. And so if you hit the moon, then some of the dust covering the surface gets blown away, and whatever's underneath can get revealed or even thrown up on top of the dust. So if there's a little bit of red over here and it looks like an impact crater, that means the real color of Styx is actually this red, and the gray is just dust on top. So, what was that?
So you made out of iron?
Well, isn't that an interesting question? Because what makes red stuff? So iron compounds make red, but so do carbon compounds. They can make red. Like those dark red tolins on Pluto, that's a different kind of red. So is this iron red? Is this carbon red? Is this a different kind of compound red? More on that when we actually know the answer, because we don't know yet. But one thing we do know is when you look at objects that are bright white, like Hydra, and I think it was, it really was just by accident. We didn't mean Hydra to be related to hydro, like H2O, like hydrothermal. Anything hydro is water related. But sure enough, there's water ice on Hydra. So we just happen to name it right. Hydra has water ice, H2O ice. And here they have, a theoretical sample of pure ice, and Hydra's not that far. Charon is pretty far. Charon has, other than the dirt from Pluto, Charon has other stuff going on. But Hydra does seem to have a whole lot of water ice. Does that mean an ice crust? Or is that just an asteroid covered with some patches of ice? Still working on that, but I tend to think it's an ice crust. And that would be interesting.
If it's solid ice, it could be a comet.
And that's the thing. When we get to this part of the solar system, which is known as the Kuiper Belt, this is beyond Neptune, so many objects there naturally are made of ice that it's not out of the question for moons and planets to have much, much more ice, not just in their crust, but in their entire makeup. And so yeah, this is still part of the ongoing exploration of this part of the solar system. We're still trying to figure out what stuff is What is it made of? What does it look like? How does it move? Why does it do all of that? And then what's the geology on the surface? Because no matter how small, there's always geology. So here's my last slide, finally. Where do we go from here? Well, Alan Stern, who I mentioned at the beginning of the talk, actually wrote a blog post about this in April. And he said, look, if we get our funding approved in August or September 2016, that's 2 or 3 months from now. If they get their funding approved, then yes, they're going to go to 2014 MU69. But they're also going to look at 20 other Kuiper Belt objects. And they're going to look for rings. Because remember, we talked about rings and ring particles? Yeah, this is the part of the solar system, but that's a real possibility. And we're going to look for other stuff, plasma and dust. We're going to look at space weather out here. That's exciting. Space weather is sun-planet interactions. So what's the weather like out here? And of course, there could be more objects that we see after MU69. Because just because the funding runs out doesn't mean the spacecraft can't work, which means maybe the funding should continue. So that's what we're hoping. Anyway, lots of references. Okay, guys, I used APA format, but always cite and reference your talks. And if you do have any questions, you can always contact me at this email address, or you can ask one of the LTO people and they'll let you know how to get hold of me. But it's always a pleasure to talk with you, so thank you guys. I will stay here for additional questions. Thank you.
Well, thank you, everybody. We will be closed during July for maintenance. And for those of you who don't know, we are an all-volunteer organization. We depend on people's donations of both time and money. So if you have more money than time, there's a donation box in the back. Or if you have more time this summer, we would welcome help as we do our annual cleaning and maintenance. And then we will have our next Star Night again on the 3rd Friday of August. And can you remind me what that talk is?
It's about radio astronomy, and it's the Square Kilometer Array in New Mexico.
That's right.
That's great. So come back for that.
And over the summer...
It's really nerdy, though.
And over the summer, we have a group of students working with the radio astronomy data that we're collecting. So thank you very much. And anybody who's interested in that, did you want to stand up and say anything about the radio astronomy program?
Silence.
Okay.
Okay, so I will just make a plug. It's awesome that LTO sponsors high school students to every summer do this work. And for those of you who are going to be in high school someday, you may want to think about it, because this is a great way to learn what it's like to be an actual scientist and work with scientists. Because a whole lot of scientists aren't paid. Unpaid volunteer science is still science. I'm a big proponent of citizen science. Guess what? You're a citizen, regardless of your age, regardless of your ability level. So be a scientist.
Well, thank you very much.